students, this is the fifth lecture of course Dam Engineering. Today we will discuss the thick cylinder theory. Now suppose this is a thick cylinder, okay, and this is the internal radius, this is the external radius, okay, and if suppose this is the upstream part, and this is subjected to pressure PE here, and if this is the internal part, so this is the pressure here is PI, okay. The thickness of this cylinder is say T. In this thick cylinder theory, we consider this our arch dam to be a part of a thick cylinder, okay. This is the modification, or you can say rather improvement in the thin cylinder theory, because practically arch dam does not behave like a thin cylinder, okay. So suppose the radial stresses of this cylinder, of a thick cylinder, is given by A by R square minus B, and the circumferential stress is given by A by R square plus B, where R is the radius of cylinder, okay, where and A and B are the constants. So in order to determine the values of these two constants A and B, we have to consider the boundary conditions. So at R is equal to Ri, means over here at R is equal to Ri, this is subjected to pressure Pi, okay. So we can say pressure P is equal to Pi, okay, and at R is equal to Re, R equal to Re means over here the pressure P is equal to P, okay. So by putting this boundary condition over here, we can have Pi is equal to A over Ri square minus B, and Pe is equal to A over Re square minus B, okay. So by solving these two equations, we can get the value of the constant A and B. So now let us solve these two. Okay, so this will be the value of A. Now by putting the value of A in one of the two equations, we can get the value of B. So let us now put the value of A over here. So we get Pi is equal to this will be the value of B. Okay. So from here we get the values of both A as well as B. Now suppose that in our arch dam there is no tailwater. So if there is no tailwater, then Pi will be equal to 0. Okay. And suppose at the upstream side the depth of water is say h. So at the upstream side Pe will be equal to gamma W times h. Okay. Let us denote with this P. So now simplify A and B, we get A will be equal to Ri square Re square. Okay, Pi is 0, so this will be minus P over Re square minus Ri, and this is B, so this will be minus Pre square over Re square minus Ri square. R since this is A over R square minus B. Okay. Similarly, for sigma C, okay, this is sigma C is A over R square plus now suppose that the sigma E is the stress, circumferential stress at extra dose, okay, and sigma I represents the stress at intradose. Okay, intradose means at R equal to Ri. So we can write it as at R equal to Re, sigma E is equal to P Re square over Re square minus Ri square. 1 plus Ri square over Re square. Okay. So this will be equal to P Re square over Re square minus Ri square Re square plus Ri square over Re square. So sigma E will be given as P Re square plus Ri square over Re square plus minus Ri square. Okay. Similarly, sigma I is equal to P R E square over R E square minus R I square 1 plus R I square over R I square. So this will be 2 twice of P R E square over R E square minus R I square. Okay. Now at now we can say that R E is equal to R I plus T. Okay. Okay. You can see from here. From here. From here, R E is equal to R I plus T. Okay. So we can we can write we can write R E is equal to R I plus T. So R I will be equal to R E minus T. Okay. So put it here, we get sigma I is equal to 2p R E square over R E square minus R E minus T whole square. So we can write it over here, R E square minus R E minus T whole square over R E equal to 2p over sigma I. Okay. And we can, this is R E square, and on separating each term we get 1 minus T over R E whole square minus 2p over sigma I equals to 0. Okay. And for the simplification, we can write it as 1 minus 2t over Re plus t over Re whole square minus 2p over sigma equals 0. So this will be 1 minus 1 plus 2t over Re minus t over Re whole square minus 2p over sigma equals 0. Okay. And this will give you t over Re whole square minus 2 t over Re plus 2p over sigma I equals to 0. So we can see from here that this represents a quadratic equation of, okay. So now the variable here is x, say t over R. Okay. So solution will be minus b plus minus the root b square minus 4ac over twice of A. Okay, so A is 1, B is -2, and C is 2P over sigma I. So if you put the values, you will get T over RE equal to 2 plus minus 4 minus 4 8 P over sigma I, okay, divided by 2. So on simplification, we can have T is equal to RE, okay, 1 plus minus 1 minus 2P over sigma I, okay. So T is equal to RE 1 minus 2P over sigma I, okay. This will be the value of thickness. This is how we can calculate thickness, okay. Now if suppose uh, we want to write the expression of thickness uh, in terms of internal radius, okay. So Ri is Re minus T, okay. So if you can put the value over here, I'm writing it directly. You can 1 minus 2P over sigma I, okay, over under root 1 minus 2P over sigma I. This is the thickness in terms of introdose, and this is thickness in terms of external radius. The expressions that we need in order to calculate the thickness of an arch dam based on thick cylinder theory, we have T in terms of external radius as 1 minus under root 1 minus 2P over sigma I, okay, where Re is external radius of an arch, T is thickness of an arch, P here is the upstream water pressure, and sigma I is the internal stresses. So remember, here we have considered the tail water pressure to be 0, okay, tail water pressure to be 0. I hope you understood how to uh, use the thick cylinder theory in order to determine the thickness of an arch, okay. If there is any query, regarding the thick cylinder theory, you can comment, post your comments on the on this video, okay, or you can ask your questions